Cool. Hello, everybody. Thanks for that. First of all, thank you very much for allowing us to speak in English. This would be terrible if I was speaking in German, so thank you. My name's Edward, and I'm the CEO of a company called Scape Technologies. And at Scape, we're building a 3D real-time map of the world that we use to precisely align digital devices with sub-centimeter accuracy. But before I get into all of that technical talk, I thought I'd start off with a little bit of a history lesson. So I'd like to throw out a question. Is there anybody in the audience that wants to have a guess at what we're looking at right here?
Map.
A map, exactly. So this is actually what we believe is one of the very first attempts at a world map. This was created in 1600 BC. And as you can see here, we've got in the center here, we have Babylon. Surrounded it is a few different cities, and then we have a river around the city itself. So this is essentially what maps do. They take a view of the world, they abstract out the meaningful components, and they present those components in a manner which is easy to understand. And what's easy to understand and what's meaningful changes over time. So for the Babylonians, all they needed to understand was how their city sat in relation to the places around it. But that changes over time. So for the Christians in the 1300s, it was more important to use maps to tell a story. So this is the Mappa Mundi that was found in Hereford. And in the very center, we have Jerusalem. Over on the left, we actually have a depiction of Noah's Ark. And up at the top, we have a depiction of God. And actually what looks like the end of the world map around the outside is actually the walls to the Garden of Eden. So the same things between these two different maps is that the depiction of space, the way these countries, these places in the map are depicted, has no relation to their geographic size. It's actually more to do with their significance. So the first attempt at unifying all the contents of a map within a single system was actually created by a Greek cartographer and philosopher called Ptolemy, who had this really innovative idea of unifying everything in the map within a grid system of vertical and horizontal lines, which today we call longitude and latitude. And this is this idea of unifying the map, which we'll come back to eventually. Now, there's one thing which all of these different maps have in common, whether it's the very first Babylonian world map, or the Christian map, or this one, or even the Google map that you have in your pocket. All of these maps were designed for humans to understand. And over the next few years, we're going to see the emergence of a new type of map which is built from the ground up for machines and computers to understand. So in the same way that what's meaningful to extract from the world changes over time, what's meaningful to extract also changes with the applications of how you want to apply that map. So for self-driving cars, for example, you need to understand precisely where you are on the road so you can make sure that you stay on the road, right? For robotics, you need to be able to quickly evaluate a scene and share the geography of that scene with another robot, for example. And for augmented reality, which is the area that we're currently focused on, it's really vital to have a one-to-one map of the world that you can use to align digital content with physical places. Because unless you know precisely where you are in the world, the digital world and the physical world simply won't align. And this is something which is necessary for all of these devices. Localization, figuring out precisely where these computing devices are in the world. So up until this point, we've used GPS. Our devices listen out for these signals which are being sent from satellites which orbit the world. But this is particularly problematic in dense urban environments where these signals get bounced around from buildings, increasing the inaccuracy of your location. So what we do at Scape Technologies is rather than using our phones to listen out from these GPS satellites, we instead compare our visual camera information with a pre-known map of the environment to triangulate precisely where we are within that environment using computer vision. And in practice, it looks a little bit like this. So what you're seeing right now is a fly-through of what we call a point cloud of Trafalgar Square in London. The only thing that was used to create this map is the video stream that you see in the bottom right-hand corner. This is essentially a 360-degree camera that we walk around. And every single point within this map represents essentially a type of barcode, a fingerprint that uniquely identifies that point to a particular location in space with very incredible accuracy. And essentially what we can do, we can compare what we see with our cameras with this pre-known map of the environment to triangulate precisely where we are within that map. And we can do this across an incredibly large scale. So in essence, this is how we might look to use this for augmented reality. Essentially, we can walk up to an environment in London, in Trafalgar Square, hold up a regular camera device, whether it's the very latest iPhone or your Android device from 5 years ago, hold it up, and by comparing the visual information with the map that we have on the cloud, we can determine precisely where that device is in order to display virtual reality or augmented reality, for example. So this is where we're at today. This is the type of technology which is going to be enabling, the dreams that we saw with the original Pokemon Go. It's the type of technology which will allow you to have digital annotations into the physical world. Imagine we've got this cache of geographical data, and we use these devices as windows to see into that world. We can use this technology for navigation, if you're in an unfamiliar space, for be able to be navigated around a particular environment. And one element that we've always talked about internally at Scape is being able to walk into the Roman Colosseum, and instead of being able to see what the ruins once looked like, you instead see what they were, with the gladiators acting out in front of you. So that's part of what we're doing at Scape, and I hope I can answer some of your questions. Thanks very much.
Come on, guys, don't be shy back there. Was the mic?
If you shout out, I can probably hear you.
Hi, I'm Andre.
Hi, buddy.
How big is the in capacity in gigabytes this map from Trafalgar Square, and how much would it be for the whole world?
Sure. So we are sitting on a tremendously large amount of data, and for various reasons I won't go into exactly how much data we're sitting upon, but it's terabytes and terabytes and terabytes and terabytes and terabytes, right? What we're trying to design is a system which is linearly scalable. So for various technological reasons, there's parts of this component where we optimize the map, which is a non-linear scaling algorithm. So basically, the more data that you have, eventually it scales exponentially, and eventually you hit up against a brick wall. What we want to have is one single funnel you can think of, where we throw in as much data as possible, and we can scale up linearly. So that is a lot of data, and it's not just data that you need to build the map in the first place. Since 2007, Google has been going around sending these cars to go and collect and hoover up data, but it's a really antiquated way to build your map, having to send out these fleets. We used to do this hundreds and hundreds of years ago when we send out people on horseback with a little artist drawing, essentially. What the holy grail for us is having a real-time 3D map that every single time it's queried, that same query keeps that map up to date. Because once you have that, that's the feedback loop, that now you have this living thing, this living map, which the more that it is used, the stronger it gets, the more robust it gets. And you're right, that means there's a huge amount of data. So you need to be able to figure out ways you can abstract the meaningful information. I talk about extracting the meaningful information from the world. You need to extract the meaningful information from the data so that you can use that for the purpose of what we call localization, figuring out where you are in the most efficient and robust way possible. Make sense? Lots of data.
Hi, how do you deal with change? I saw trees in your 3D rendering and stuff like that. That will change over time.
So that was a point cloud fly-through that we made summer last year. What we now have is an extra level of semantic segmentation. So You might have seen things where you point a camera at something and it will tell you it's a car or an apple or a tree. So what we now do is we use that to our benefit, so that the only things within the map are actually things which benefit us for localization. Obviously, a scene looks very different as you change the seasons, and for using visual information to localize, looking at a tree isn't going to be that useful. But if you understand that that's a tree and it has a tree trunk and that's relatively stable, you can actually use that to help how you use that information to localize.
In Europe, we mostly live above the ground. In Asia, a lot of parts of the cities tend to be underground. Would this work indoors?
Yeah.
How do you determine the first base point of where you are?
So the current status of things, indoor is kind of where everyone's having this current battle with augmented reality, because you have the benefit of using different types of sensors, like almost like the 3D sensor that you see in the latest iPhone. You have these 3D sensors that can project light out into the world, and that helps you build very accurate maps indoors very easily, but it doesn't work so well outdoors. So right now you can do this indoors with these types of sensors, but our vision is to have this kind of one unified map that is aligned to geographical reference frames. So you could use 3D sensors inside to kind of align yourself to an arbitrary starting point, and you have this kind of, you don't necessarily know where this 3D map is positioned in space, but you know everything relative within that map. Our vision is just to have one single one where everything is aligned to the geographical reference frame, and there's all sorts of things you can do to align where those indoors maps are aligned to outdoors. Like you can look at the various windows. There's some research which is seen, right, if you have a map indoors where you see where the windows are, and you have a map outdoors where you can see where the windows are, you can use that information to triangulate how those maps sit internally. Does that make sense?
Makes a lot of sense, but how do you determine the base point? Because you must start somewhere, and commercial GPS is at least accurate to maybe a couple of meters at best. So how do you determine that base point?
We have a patent on that, which means I can't go into too much detail. Apologies.